Good morning to one and all present here. Today we are going to see the topic about stress strain relationship for solids. It is about the normal thing to we consider with the bar element. Uh, Mainly we are seeing that there is normal stress, normal strain, and a Poisson ratio, shear stress, shear strain. In this, the normal stress will be on to how much area the stress is acting. So here the formula is axial stress sigma is equal to force by area, or you can say that as load by area. Mainly there is an axial force which is acting left side and the right side of the bar. It is like a pulling or pushing. This one is tensile stress applied to a rod. It is also known as pulling the rod or bar. At the right hand side, it is known as compressional stress applied to a rod, which is pushing the rod. Okay, so there are two types. One is tensile stress, and another one is compressional stress, or we can say that compressive stress. The main formula is about stress is equal to stress sigma. Stress sigma is equal to force by area, which has a units of lb by inch square or newton per meter square. We are always consider that newton per meter square only, and also 1 bar is equal to 1 newton per meter square. Here we are considering the cross sectional area and the length of the rod, and also force is perpendicular to the area. And the definition of normal strain will be, we can say that in simple way, it is a strain eta is equal to del L by L, that is change in length by original length. Change in length by original length. This is the definition of normal strain, and we have to consider that with the original length and a change in length. The second two diagrams are LO is known as original length and LO plus del L, that is change in length. After pulling the rod, it is giving you some extension of the rod, or we can say it will give you the extra dimension. The length is 8 mm, means after that it will give you 10 mm. That is known as change in length. So this change in length to original length ratio will be, we are saying that strain, that is normal strain. First one is normal stress we saw, and now it is normal strain. The third one is Poisson's ratio. Poisson's ratio is one ratio which is having the emblem of or symbol of eta, okay, or nu we can say, or nu we can say. It is known as, if it is compressive, means compressive stress by compressive strain, like that. Okay, next thing is shear stress. Shear stress is not different from the normal stress. It is just a shearing forces acting. Previously there is an axial force acting, now it is shear force. So shear force simple is tau we can say, or T we can say. In this T they are putting T is equal to force by original area. This force is known as shear force. This is the shear symbol. If it is like pulling, we saw that in the bar, right? In the bar we saw that pulling forces, and in that pulling forces, here if we pull that upper and lower, means it will become couple, or it will give you the rotating motion. That is known as shear stress results from a force couple. Second one is shear stress tends to deform an object as shown. The whole object is tilting. This one is couple, also known as rotating. The B will be shear stress tends to deform an object as shown. The object is tend to tilt, or you can say it is sloping, kind of like that. Okay, and the last one is definition of shear strain. The same only, del L by L only, but here the original length will be changed into two types, right? One is couple and another one is deformation. First one is couple, second one is deformation. So here we are using that shear strain notation as y is equal to tan theta is equal to same del L by L or del X by L, that is change in length by original length. Here it is area, so del X they are using. Next one is, by means of the tensile stress we can analyze the results. How much tensile forces are acting in the rod, we can get the formula as practical. It is application oriented. Tensile testing machine is there, UTM is there, universal testing machine. In that we can analyze that. Next one is uniaxial. I told that at single point, normal stress and normal strain, right? Those are with the single point they are pulling the forces with the rod. But here it is uniaxial, that is same forces acting everywhere to pull the rod. So stress strain relationship will be here, eta xx, that is x it is pulling, so eta xx equal to 1 by Young's modulus. E is known as Young's modulus into stress, or you can say that Young's modulus formula, you already know that Young's modulus will be stress by strain. So that is interchanged into this. Okay, next one is transverse strain. Transverse strain is also linked to that. Okay, next one is stress strain curve. Stress strain curve gives you the materials behavior. First one is about, if we are getting the concrete, means at the same time we are applying stress and strain, or putting some forces or putting some load, everything, means it will give you the concrete as little bending line, that is, it is strengthy. Concrete is strengthy compared to the cast iron. Cast iron is little more bending. So concrete, cast iron and mild steel. Mild steel has a proportional limit. This mild steel only we are seeing in the stress strain curves. That has a elastic limit, proportional limit. Last one is extreme limit, like that. Okay. So whenever we are taking mild steel, see this diagram, stress strain curve, ductile material, that is mild steel is a ductile material. So these are the elastic behavior and the plastic behavior. This first diagram, right, this first diagram having a last line for mild steel. The same diagram is explained in detail. So this is the elastic behavior and the plastic behavior. This line is this graph is known as stress strain curve again. So first point when we are applying load, it move into a elastic region, which is elastic, means it regain to itself whenever we are remove the load. So elastic region. After that elastic region, it will be a yield. Before elastic limit, it is known as proportional limit. There is proportional limit and the elastic limit. Third one is yield strength. So this place it is yielding, slowly yielding. Next thing is strain hardening till the ultimate stress. So yield stress to ultimate stress, it is giving you the yielding at strain hardening. The last one is necking. Necking means it is going to break. So last one is necking. Finally it is fracturing here, fracture. So we are taking four things. First one is ultimate stress, sigma u, ultimate stress, and the second one is fracture stress, and the third one is yield stress, and the fourth one is proportionality limit. Okay, these are the main things. And for brittle material, it is directly going to break. Nothing is happening. Brittle, you know that, right? Glass. Whenever we are applying some load or stress, it will break. That's all. Okay. And third example is stress strain curve for low carbon steel. Low carbon steel also same like first one, but here we are taking these four, and here it is about the strength, ultimate strength, yield strength, that 1 2 3 4 5, 1 2 3 4 5. You see that, sorry, 1 2 3 4 5, these are the things. Ultimate strength, yield strength, third one is rupture, fourth one is strain hardening, fifth one is necking region. So the Hooke's law is nothing but the same only, the Young's modulus is equal to stress by strain, or we can say E is equal to sigma by small e, that only. Okay, so finally the plastic region. The region of stress strain curve you have to understand. Stress strain curve will be mainly we are getting that elastic region. Till the elastic region, it can regain to its original position, but after plastic region, it is nothing but a bended or changed or deformed position. That's all. Finally, it will be a failure point. So similar to pressure volume curve, previously we are seeing that stress strain curve. Here it is pressure volume curve. So here area is equal to work. That's all the stress strain relationship. These are the important topics in stress strain relationship for solids in mechanics of materials. Thank you so much for watching this.